HTTP/3. The next generation of the web. Welcome to the channel. Please consider subscribing. I produce videos daily, covering a wide variety of cloud topics, with a focus on networking. Also, hit the bell icon to get notified of new videos. Today, we're exploring HTTP/3, the latest evolution of the protocol that powers the World Wide Web. This isn't just a minor update. It's a fundamental shift in how browsers and servers communicate, designed to make your web experience faster, more reliable, and more secure. We will unpack what HTTP/3 is, why it was necessary, and how its underlying technology, QUIC, is changing the game. By the end of this presentation, you will understand the profound impact HTTP/3 is having on the Internet's infrastructure. Agenda. What we'll cover. To guide our journey, we have structured this presentation into 5 main parts. We will begin by looking at the evolution of HTTP, understanding the limitations of past versions that created the need for HTTP/3. The second and most substantial part will be a deep dive into QUIC, the new transport protocol that serves as the foundation for HTTP/3. It is impossible to understand HTTP/3 without understanding QUIC. Next, we'll focus on the specifics of HTTP/3 itself, seeing how HTTP concepts are mapped onto QUIC. Then, we'll discuss the real-world impact, looking at performance, security, and the current state of adoption. Finally, we'll wrap up with a summary of the key takeaways and a look at the future beyond HTTP/3. The evolution of HTTP. The Hypertext Transfer Protocol, or HTTP, has come a long way since its inception. HTTP/0.9 in 1991 was incredibly simple, designed just to transfer HTML files. HTTP/1.0 introduced concepts like headers and different content types. HTTP/1.1, standardized in 1997, was the workhorse of the web for 2 decades. It introduced critical features, like persistent connections, but it had its own performance bottlenecks. HTTP/2, standardized in 2015, was a major leap forward, introducing multiplexing to allow multiple requests and responses over a single connection. However, it was still built on TCP, which led to a new kind of performance problem. This set the stage for HTTP/3, which fundamentally changes the transport layer to finally solve these long-standing issues. HTTP/1.1: the foundation. For over 20 years, HTTP 1.1 was the engine of the web. Its biggest innovation was the persistent connection, allowing a browser to reuse the same TCP connection to a server to download multiple resources like images and scripts, rather than opening a new connection for every single item. This was a huge efficiency gain. However, it had a strict request-response model. A client had to wait for one response to complete before the next request could be fully processed on that connection. This led to head-of-line blocking at the application layer. To work around this, browsers would open multiple, typically 6, TCP connections per domain, but this added its own overhead. A big leap. HTTP/2. HTTP/2 was designed specifically to solve the application layer head-of-line blocking of HTTP/1.1. It introduced the concept of binary framing and streams. This allowed a browser to interleave multiple requests and responses over a single TCP connection, a feature called multiplexing. As you can see in the diagram, the browser can send a request for index.html and, without waiting, also send requests for style.css and script.js. The server can then send back the responses as they become available, with their data frames interleaved. This was a massive improvement, significantly reducing page load times by making much more efficient use of a single connection. The lingering problem. TCP's head-of-line blocking. While HTTP2 solved head-of-line blocking at the application layer, it revealed a new bottleneck at the transport layer. All those independent HTTP2 streams were multiplexed over one single, ordered TCP connection. TCP guarantees that packets will be delivered to the application in the exact order they were sent. This means if a single TCP packet is lost in transit, the entire connection has to pause. As the diagram shows, even if packets for the CSS and JS streams have arrived successfully, the operating system cannot deliver them to the browser until the lost packet containing data for the HTML stream is retransmitted and arrives. We solved one head-of-line blocking problem only to be stuck with another, deeper one. Introducing HTTP/3. This is the core problem that HTTP/3 was created to solve. The IETF recognized that to get true multiplexing without head-of-line blocking, they had to move away from TCP. The solution was HTTP/3. A new version of the protocol that does not run on TCP at all. Instead, HTTP/3 runs on top of a new transport protocol called QUIC. As we will see, QUIC provides its own streams that are fully independent at the transport layer. By building HTTP on top of QUIC, we can finally achieve the full potential of multiplexing, where the loss of data for one resource never impacts the delivery of others. This is the single most important architectural change in HTTP/3. Why a new version? Core goals. The development of HTTP/3 was driven by a clear set of goals. These goals aimed at addressing the shortcomings of its predecessors in the context of the modern web. The primary objective was to reduce latency, both in setting up connections and in transferring data. This is achieved by QUIC's faster handshake and by eliminating head-of-line blocking. Improving security was another key driver. HTTP/3 mandates encryption and leverages the modern security features of TLS 1.3. Finally, it was designed to provide a better experience for mobile users, with features that allow connections to survive changes in the device's network address. All these goals are realized through its foundation, the QUIC protocol. The new stack. This diagram clearly illustrates the fundamental shift in the protocol stack. On the left, we have the familiar stack used for HTTP/1.1 and HTTP/2. The application protocol runs on top of TLS for security, which in turn runs on top of TCP for transport reliability. This entire stack is built on the Internet Protocol, IP. On the right is the new world of HTTP/3. TCP and TLS are gone, replaced by a single, integrated protocol, QUIC. QUIC provides both the security of TLS 1.3 and the reliable transport features of TCP, but it does so on top of the much simpler UDP protocol. This new, streamlined stack is the key to HTTP/3's performance and flexibility. HTTP/3 is powered by QUIC. It's crucial to understand that most of the groundbreaking features we associate with HTTP/3, like the faster handshake, connection migration, and the absence of head-of-line blocking, are not actually features of HTTP/3 itself. They are features of QUIC, the transport protocol underneath. HTTP/3 is the application mapping layer. It defines how HTTP semantics, like requests, responses, and headers, are expressed using QUIC streams and frames. Therefore, to truly understand what makes HTTP/3 special, we must first spend some time understanding its engine, QUIC. The next section of our presentation will be a deep dive into this foundational protocol. What is QUIC? Welcome to the second part of our presentation. So, what is QUIC? QUIC stands for QUIC UDP Internet Connections. It is a modern, general-purpose transport layer protocol, initially developed by Google and now standardized by the IETF. As its name suggests, it runs over UDP. QUIC's design philosophy is to take all the good parts of TCP, like reliability, congestion control, and flow control, and re-implement them from scratch in a more efficient and flexible way. At the same time, it integrates the cryptographic features of TLS 1.3 directly into the protocol, ensuring that every connection is secure by default. It is this combination of a modern transport and built-in security that makes QUIC so powerful. Why UDP? Choosing to build QUIC on top of UDP might seem counterintuitive, as UDP is unreliable. However, this is QUIC's secret weapon. TCP is implemented deep within the operating system's kernel. Changing TCP is incredibly difficult and slow, as it requires updates to billions of devices. This has caused TCP to ossify, or become resistant to change. By using UDP, QUIC moves all the complex transport logic, reliability, congestion control, and so on, out of the kernel and into user space, as part of the application or its libraries. This means QUIC can be updated and improved as easily as updating your browser. It allows for rapid innovation and experimentation, freeing the transport protocol from the slow pace of operating system updates. QUIC streams. The solution to HOL blocking. The most important feature that QUIC provides for HTTP/3 is its native support for multiple, independent streams. As we discussed, this is the definitive solution to the transport layer head-of-line blocking problem. Within a single QUIC connection, an application can create many lightweight streams. Each stream provides a reliable, in-order flow of bytes, but there are no ordering guarantees between streams. The loss of a packet carrying data for one stream has absolutely no impact on the delivery of data for any other stream. This allows an HTTP/3 browser to download all the resources on a page with maximum parallelism and efficiency. Visualizing stream independence. This diagram makes the benefit crystal clear. In the top half, we see the old HTTP/2 over TCP scenario. A single lost packet for the red stream forces the blue and green streams to wait, even though their data has already arrived. The entire connection is stuck. In the bottom half, we see HTTP/3 over QUIC. The packet for the red stream is lost, but it doesn't matter to the other streams. The QUIC layer can immediately deliver the data for the blue and green streams to the browser for processing. Only the red stream is temporarily paused. This fundamental difference results in significantly faster page load times, especially on networks with high latency or packet loss. The QUIC handshake. Speed is key. Another major advantage QUIC brings to HTTP/3 is a dramatically faster connection setup. QUIC merges the transport handshake and the cryptographic handshake into a single process. For a brand new connection to a server, QUIC can establish a fully authenticated and encrypted session in just a single round trip, 1 RTT. This is a huge improvement over the classic TCP plus TLS model, which often required 2 or even 3 round trips before the first byte of application data could be sent. By shaving off 1 or 2 entire round trips from the initial connection, QUIC significantly reduces the initial latency that users perceive when visiting a site for the first time. 0 RTT resumption. For users who are returning to a site they have recently visited, QUIC can be even faster. It supports a 0 round trip, or 0 RTT, connection resumption. During the first connection, the server can give the client a special cryptographic ticket. On the next visit, the client can use this ticket to encrypt its first HTTP request and send it along with the very first handshake packet. The server can use the ticket to decrypt the request and start working on the response immediately, while the rest of the handshake completes in the background. This can make websites feel almost instantaneous for repeat visitors. Security by default. Integrated TLS 1.3. QUIC was designed with the philosophy that security should not be an afterthought. It fully integrates the robust security of TLS 1.3, and encryption is mandatory for all connections. There is no such thing as an unencrypted QUIC or HTTP/3 connection. This means that all HTTP/3 traffic is automatically protected with confidentiality, integrity, and authentication. This always encrypted approach simplifies deployment for developers and provides a massive privacy win for users, as it prevents passive network observers from snooping on web traffic. The key derivation ladder. To achieve its always encrypted state, QUIC uses a sophisticated, multi-stage key derivation process. It doesn't use just one set of keys. It uses a series of progressively stronger keys as the handshake proceeds. The process starts with initial keys, derived from public information, to provide basic obfuscation for the first packets. After the Diffie-Hellman key exchange, much stronger handshake keys are derived to protect the rest of the handshake. Finally, once the server is authenticated, the final 1 RTT application keys are derived to protect the actual HTTP data. This key ladder ensures that each phase of the connection is protected with keys appropriate for its level of security. Connection IDs. Solving mobility. One of QUIC's most revolutionary features is its solution to the mobile connectivity problem. A TCP connection is tied to the client's IP address. If that address changes, for instance, when a phone switches from Wi-Fi to a cellular network, the TCP connection breaks. QUIC solves this by identifying connections with a connection ID, CID, instead. The CID is simply a random number that remains constant for the entire life of the connection. If the client's IP address changes, it simply starts sending its QUIC packets from the new IP address, but with the same CID. The server sees the familiar CID and knows it is the same connection, allowing it to seamlessly migrate to the new network path without any interruption. Connection migration in action. This diagram shows the connection migration process. The client starts a connection from its Wi-Fi IP address, IPA, using connection ID 72. The device then moves and switches to the cellular network, getting a new address, IPB. The client then sends a QUIC packet from IPB, but it still includes the same CID, 72. The server receives this and realizes the connection has moved. To prevent malicious actors from hijacking the connection, the server sends a small challenge to the new address. The client responds, proving it controls IPB, and the server validates the new path. The HTTP/3 data transfer can then continue uninterrupted, as if nothing happened. Reliability on UDP. QUIC re-implements the reliability features of TCP from scratch. It has a robust system for tracking which packets have been sent and which have been acknowledged by the receiver. When a packet is detected as lost, QUIC ensures that the data contained within that packet is retransmitted. It's important to understand that QUIC retransmits the data, not the original packet. The data from the lost frames is placed into a new QUIC packet with a new packet number. This avoids certain ambiguities that can occur in TCP's retransmission logic and makes for a more robust recovery process. Advanced acknowledgements. QUIC's acknowledgement mechanism is more expressive and provides more information than TCP's. An ACK frame in QUIC explicitly lists ranges of packet numbers that have been received. This makes it very resilient to packet reordering and gives the sender a very precise picture of what the receiver has seen. Furthermore, every ACK frame includes the delay between when the acknowledged packet was received and when the ACK was sent. This gives the sender a constant stream of high-quality round-trip time, RTT, measurements, which are crucial for quickly detecting lost packets and for feeding into the congestion control algorithm. Pluggable congestion control. Congestion control is the algorithm that prevents a sender from overwhelming the network. A major benefit of QUIC's userspace design is that its congestion control is pluggable. Different applications can choose or even design different algorithms best suited for their needs. The default algorithm is similar to TCP's new Reno. However, Many large providers use more advanced, modern algorithms. For example, Google uses BBR, which stands for bottleneck bandwidth and round-trip propagation time. It is designed to be more accurate and efficient on modern networks. This flexibility to rapidly deploy and test new congestion control algorithms is a huge long-term advantage for QUIC. Flow control in QUIC. To prevent a fast sender from overwhelming a slow receiver, QUIC implements flow control at two levels. There is per-stream flow control, where the receiver advertises how much data it is willing to buffer for each individual stream. This prevents a single large download from hogging all the memory. There is also connection-level flow control, which limits the total amount of buffered data across all streams combined. This two-level system gives the receiver fine-grained control over its memory usage, making the connection more stable and resilient. Quick summary. So, to quickly summarize this section, QUIC is the engine that gives HTTP/3 its superpowers. It provides a fast 0/1 RTT handshake, eliminates head-of-line blocking with independent streams, and ensures connections are robust on mobile networks through connection migration. It achieves all of this while being secure by default, with mandatory TLS 1.3 encryption. And its user space design allows for rapid innovation in areas like congestion control. With this foundation in place, we can now look at the specifics of the HTTP/3 protocol itself. Mapping HTTP to QUIC. Welcome to the third part, where we will focus on HTTP/3 itself. Now that we understand the powerful features QUIC provides, the job of the HTTP/3 specification is actually quite simple. It primarily defines how the familiar concepts of HTTP, requests, responses, headers, and bodies, are mapped onto the streams and frames provided by QUIC. This mapping is designed to be very similar to the one used in HTTP/2, which makes it easier for developers and server implementers to transition. However, it has been adapted to work with QUIC's stream-based architecture and to solve some of the subtle issues that arose with HTTP/2. Requests and responses on streams. The mapping is very straightforward. Each HTTP request and its corresponding response are exchanged on a single, dedicated QUIC bidirectional stream. The process is as follows. The client opens a new bidirectional stream and sends its request on it. The server then processes the request and sends the response back on the same stream. Because each request-response pair gets its own stream, they are all completely independent. A slow response for a large resource on one stream will never delay a fast response for a small resource on another stream. The client can open as many streams as it needs to fetch all the resources for a page concurrently. HTTP/3 framing. Just like HTTP/2, HTTP/3 is a binary protocol that uses a system of frames to convey information. However, the framing layer in HTTP/3 is simpler than in HTTP/2, because QUIC already handles many of the transport level details, like stream management. The two most fundamental frame types are headers and data. A headers frame is used to send the HTTP request or response headers. After the headers frame, one or more data frames carry the actual message body, such as the HTML document or a JPEG image. There are other control frames as well, but these two are the workhorses of HTTP/3. Headers and QPACK. HTTP headers can be quite verbose and repetitive. To reduce this overhead, HTTP/3 uses a specialized compression scheme called QPACK. The compressed headers are sent in one or more headers frames. QPACK is the spiritual successor to HPACK, the header compression algorithm used in HTTP/2. However, it was redesigned specifically for QUIC. HPACK relied on the strict in-order delivery of TCP, which doesn't exist with QUIC's independent streams. QPACK was developed to provide robust and efficient header compression in a world where data can arrive out of order. What is QPACK? QPACK solves the out-of-order stream problem in a clever way. Like HPACK, it uses dynamic tables to store frequently seen headers. However, it decouples the sending of compressed headers from the instructions that update the dynamic table. The table update instructions are sent on their own dedicated unidirectional stream. This ensures that the state of the dynamic table is always consistent, even if the headers frames on the request streams arrive out of order. This allows QPACK to achieve excellent compression ratios without being vulnerable to the head-of-line blocking that would occur if a header's frame had to wait for a table update. DATA frame. The DATA frame is the simplest but most common frame type in HTTP/3. Its purpose is to carry the payload, or body, of an HTTP message. After a client sends a HEADERS frame with its GET request, the server will respond with its own HEADERS frame, followed by one or more DATA frames containing the requested content, such as the HTML of a web page. There is no complex logic in the DATA frame itself. It is simply a container for a chunk of the message body. The QUIC layer below is responsible for ensuring that all these chunks arrive reliably and are delivered to the application in the correct order for that particular stream. Server push in HTTP/3. HTTP/3 retains the server push feature from HTTP/2, although its usage in the real world has been limited. Server push allows a server to proactively send resources to a client that it anticipates the client will need, without waiting for the client to request them. In HTTP3, the process starts with the server sending a push_promise frame on a request stream. This frame signals the server's intent to push a resource. The actual resource data is then sent on a separate, newly created unidirectional stream initiated by the server. This design neatly maps the concept of a server-initiated transfer to QUIC's unidirectional streams. Prioritization. Controlling the priority of different resources is essential for good web performance. For example, a browser needs to load CSS and fonts before it loads images at the bottom of the page. In HTTP/2, prioritization was a complex part of the protocol itself. HTTP/3 simplifies this by making prioritization an application-level concern. The HTTP/3 application can send priority information, using for example the extensible priorities scheme, to the QUIC transport layer. It is then up to the QUIC implementation to use this information to decide how to allocate bandwidth and which data to send first. This separation of concerns makes the system more flexible. From HTTP/2 to HTTP/3, key differences. This table provides a concise summary of the key upgrades HTTP/3 offers over HTTP/2. The most fundamental change is the transport. HTTP/2 is reliant on TCP, while HTTP/3 uses the much more advanced QUIC. This single change is the root cause of the next major difference. HTTP/2 suffers from TCP head-of-line blocking, while HTTP/3 eliminates it entirely. The handshake is another area of improvement, with QUIC's 1RTT handshake being significantly faster than the TCP plus TLS combination. Finally, the header compression scheme has been updated from HPACK to QPACK, which is specifically designed to work with QUIC's out-of-order stream delivery. Each of these changes contributes to a more performant and robust protocol. Example: loading a web page with HTTP/3. Let's visualize how a browser would use HTTP3 to load a web page. It all happens over a single QUIC connection to the server. The browser opens a bidirectional stream to request the main index.html file. As it starts receiving and parsing the HTML on that stream, it discovers references to other resources. It then immediately opens new, concurrent streams for each of these resources. One for the CSS file, one for the JavaScript, and several more for the images. Data for all these resources flows back from the server, interleaved, over the single connection. If a packet carrying part of image2.png is lost, it only affects that one stream, and the browser can continue to render the rest of the page using the data from the other streams as it arrives. Performance gains. Real-world impact. We're now in our fourth section, looking at the real-world impact of HTTP/3. The theoretical benefits are clear, but do they translate into actual performance gains? The answer is a resounding yes, especially on networks that are less than perfect. On networks with high latency or packet loss, which are common on mobile and satellite connections, HTTP/3's superior loss recovery and elimination of head-of-line blocking provide dramatic improvements in page load time. For users on these challenging networks, websites can feel significantly faster and more responsive. Even on good networks, the reduced connection setup time from QUIC's faster handshake provides a noticeable speed-up. Latency reduction breakdown. This diagram breaks down where HTTP/3 saves time compared to HTTP/2 over TCP. The biggest saving comes from the initial connection setup. The 1RTT/QUIC handshake shaves off at least one full round trip compared to the TCP and TLS handshakes, which can be a huge win on high latency networks. The second major area of improvement happens during data transfer. When packet loss occurs, QUIC's more precise acknowledgements and lack of head-of-line blocking mean the connection can recover much more quickly. Data on unaffected streams continues to flow, minimizing the performance impact of network hiccups. Security enhancements. HTTP/3 also represents a significant step forward for web security. The biggest enhancement is simply that encryption is mandatory. By running on QUIC, which integrates TLS 1.3, every single HTTP/3 connection is secure by default. This closes the door on insecure HTTP and the types of man-in-the-middle attacks it enables. Furthermore, because more of the transport protocol, like packet numbers, is encrypted, HTTP/3 leaks less metadata to network observers than TCP does. This improves user privacy. It is also more resilient to certain types of attacks, like protocol downgrade attacks, thanks to the robust version negotiation mechanism built into QUIC. The ossification problem. One of the long-term strategic benefits of HTTP/3 is that it helps combat network ossification. For years, network middleboxes, like firewalls and NAT gateways, have been built with the assumption that web traffic runs over TCP on port 443. These devices would often block or interfere with any traffic that didn't look exactly like TCP. This made it nearly impossible to deploy new transport protocols or even new features for TCP by running over UDP, which is generally allowed through firewalls. QUIC and HTTP/3 create a new, encrypted tunnel that these middleboxes cannot inspect or interfere with. This clears the way for continued innovation in the Internet's transport layer. Challenges to adoption. Despite its many benefits, the rollout of HTTP/3 has faced a couple of challenges. The main challenge is that some corporate or institutional networks have very restrictive firewall rules that block all UDP traffic, except for specific applications like DNS for users on these networks. HTTP/3 simply won't work. Another consideration is the performance on the server side. Because QUIC's logic runs in user space instead of the highly optimized OS kernel, it can consume more CPU per byte transferred than TCP for massive scale services. This CPU overhead is a factor. However, extensive optimization work in popular QUIC libraries has significantly reduced this gap over time. Fallback to TCP. To deal with environments where QUIC might be blocked, HTTP/3 has a robust fallback mechanism. A server that supports HTTP/3 will advertise this fact to the browser using an Alt-SVC alternative service header in an HTTP/1 or HTTP/2 response. This header tells the browser, "Hey, for future requests, you can also find me over there using HTTP/3 on that UDP port." The browser can then attempt to open an HTTP/3 connection in the background. If it succeeds, it will use it for subsequent requests. If it fails, for example, because UDP is blocked, it will simply continue using the existing HTTP/2 or HTTP/1.1 connection over TCP. This ensures that the adoption of HTTP/3 doesn't break access to websites for any users. How to know you're using HTTP/3? It's easy to check if you're currently using HTTP/3. You can open the developer tools in a modern web browser, like Chrome, Firefox, or Safari, and go to the Network tab. When you load a website, you can look at the protocol column. If the site supports HTTP/3 and your network allows it, you will see entries like H3 or H329, indicating that the resources were fetched over HTTP/3. If you see H2, you are using HTTP/2. Many browser extensions are also available that simply put an icon in your toolbar to show you the protocol in use for the current page. Current state of adoption. HTTP/3 is no longer an experimental protocol. It is a mature IETF standard, RFC 9114, and is already widely deployed. As of today, it is supported by default in all major web browsers, including Chrome, Firefox, Safari, and Edge. On the server side, it has been embraced by all the major players that carry a significant portion of the world's web traffic. CDNs like Cloudflare, Google, and Akamai have been instrumental in driving its adoption, making it easy for any website to enable HTTP/3 with the flick of a switch. As a result, a very large percentage of web traffic is already being served over HTTP/3 today. Ecosystem support. A healthy protocol needs a healthy ecosystem of tools and libraries. The HTTP/3 ecosystem is now very mature. There are numerous open-source QUIC and HTTP/3 libraries available for a variety of programming languages, such as Quiche from Cloudflare in Rust, QUIC from Microsoft in C, and QPACK in Python. These libraries have been integrated into popular web servers. The Caddy web server was one of the first to offer out-of-the-box support, and now both NGINX and the Apache HTTP server also have stable support for HTTP/3. This broad support makes it accessible for anyone running their own web server to start using HTTP/3. Is HTTP/3 the end of TCP? With all of this momentum, it's natural to ask, does HTTP/3 mean the end of TCP? The answer is no, not at all. TCP is an incredibly robust and versatile protocol that is the foundation for countless other Internet applications beyond the web, such as email, SMTP, SSH, and databases. HTTP/3 and QUIC were specifically designed to solve the problems of modern, secure, multiplexed web traffic. For this specific use case, it is a superior solution. But TCP will continue to be a vital part of the Internet for many other applications for the foreseeable future. The right way to think about it is that we now have another powerful tool in our networking toolbox, and we can choose the best tool for the job. Summary. Why HTTP/3 matters. Let's begin our conclusion by summarizing why HTTP/3 is such an important milestone for the web. It can be boiled down to 3 key benefits. First, it's simply faster. It reduces latency through quicker handshakes and by eliminating the head-of-line blocking that slows down HTTP/2. Second, it's more reliable, especially for mobile users. The connection migration feature means that your browsing session or video stream won't be interrupted just because your device switches networks. Third, it's more secure. With mandatory, built-in encryption, it raises the baseline for privacy and security for all web users. These three improvements together create a significantly better user experience. Beyond the browser. While HTTP/3's development was driven by the needs of web browsers, its benefits are not limited to them. HTTP has become the de facto protocol for a huge number of Internet services, most notably APIs. The vast majority of mobile apps, microservices, and IoT devices communicate using HTTP APIs. All of these applications can benefit from HTTP/3's lower latency and improved reliability. A mobile app using an HTTP/3 based API will feel snappier and will be more resilient to network changes. As HTTP/3 adoption continues to grow on the server side, we can expect to see it become the standard for all types of HTTP-based communication, not just traditional web browsing. Key takeaways. Let's distill our presentation down to the most critical takeaways. On the performance front, the key message is that HTTP/3 fixes head-of-line blocking. It does this by using QUIC, a new transport protocol built on UDP. This new foundation allows for truly independent, multiplexed streams. In addition to solving the HOL blocking problem, the integrated QUIC handshake provides a much faster connection setup, with 0 RTT or 1 RTT times, further reducing perceived latency for users. Key takeaways, Part 2. Focusing on robustness and security. The second key takeaway is that HTTP/3 is secure by default and built for mobility. It achieves this by integrating TLS 1.3 directly into its transport layer, QUIC, making every connection encrypted and authenticated. Furthermore, QUIC's use of connection IDs instead of IP addresses to identify connections is a game changer for mobile devices. This allows an active HTTP/3 connection to seamlessly migrate across different networks, like Wi-Fi and cellular, without any disruption. This combination of inherent security and network resilience makes HTTP/3 a truly modern protocol. Conclusion and thank you. In conclusion, HTTP/3 is the result of decades of learning from the successes and limitations of previous web protocols. By bravely moving away from TCP and embracing a new, modern transport layer in QUIC, it solves long-standing performance bottlenecks and provides the features needed for the next generation of Internet applications. It delivers a web that is faster, more secure, and more reliable for everyone, from users on high-speed fiber to those on patchy mobile networks. HTTP/3 is not just an incremental update, it is the future of the web. Thank you for your attendance. Please consider subscribing to the channel.